Okay, hello everybody. So as Darna said, my name is Alex. I work at Outreach in the search team, and I worked for a long time as a C++ developer, and several years I was a readability reviewer. So I was looking at usage of C++ and advising people on how to write readable and performant code. And one thing I noticed when I transitioned to Go is that people often don't pay so much attention to memory. So that's why that motivated me to make this call, which focuses on memory in the context of performance. Because in the context of correctness, in C++, you need to take a lot of care about memory. In Go, you have a garbage collector, you have much more safety. But in case of performance, it's still important to know about memory. So I'll start talking about how a computer looks like, CPU, caches, memory. Then I will focus on caches because that's the important part of today's talk. And for memory locality, which means localizing things together in memory, I'll show some benchmarks, some examples, and then I'll do some advanced topics around cache lines and around aliasing. And I'll mention the differences of allocating things on the stack and on the heap. And in the end, I'll give some tips that I think might be helpful for you to write code that's performant. So if we go back into history, we can see that the trend of increasing the number of transistors, the Moore's law, is exponential. The Y scale is logarithmic, so it increases continuously. But single-threaded performance of a single CPU core or a thread, and basically stopped going up so high, and the frequency pretty much leveled. Power dissipation or power consumption of CPUs also pretty much leveled. But what kept rising is the number of cores. So instead of having more performance single cores, we have more cores. So the performance is still going up, but just not single thread performance. But what is also important that while CPU performance increased a lot since 1980s, the speed of memory didn't go up as much. So the gap between how fast processor can process data and how fast it can get them and write them to memory keeps increasing. So this is, for example, some example in the last 25 years, how fast how much faster the memory became. And you can see that the latency numbers haven't improved much. And essentially, even the newest standard of consumer grade memory, DDR5, has higher latency usually than we had in 2007. And this is just part of the memory latency that's on the memory chip. There is more latency introduced in the CPU, but you can see just the comparison that the numbers are not really going up much. So what can we do? Here, caching goes to the rescue. In the 70s or even 80s, CPUs didn't really need a cache. They could just read data from memory, write data from memory, and everything was fine. But now we do need cache, which sits between the memory and the CPU. You can see that the access time to cache is much faster. Also, the throughput, how much data we can get from the cache, is much better. The cache serves basically as a desk where you can put books that you read from a library on your desk to access the most frequently used data fast. But the problem with caches is they are expensive. Per byte, they are orders of magnitude more expensive. So the desk can be only made very small, while the library, the total RAM is quite big. Here is how it looks like. the various shades of green are the different caches. Some sit next to the CPU cores, some are shared, and they have another function of synchronizing data access between different cores. And if one core writes some data and another core needs to read it, it can go through cache. And the cache takes care of like notifying each core that some piece of data was written somewhere else, and it needs to update it. So how good are caches performance-wise? Here you can see some benchmark. I don't know which one. I took this slide from an article, but it's some benchmark where you can increase the data size. And you see that up to 32 kilobytes of data size, it was quite fast, and that's exactly where it was able to put the data into the L1 cache. Then it got progressively slower, and you can see like one of the CPUs had much bigger L3 cache, like the largest and slowest cache. So it was able to be quite fast until much larger chunks of data. But still after that, like all the CPUs got slow as the memory, which is basically like 2 orders of magnitude slower than the cache. So in practice, if we want to test something, we need to benchmark it. In Go, it's easy. You just create a test file, you create a benchmark something function, and you run go test -bench. And I chose a very simple example that basically sums numbers from 1 to n. And I made some differences. So first example is a very simple one. It just takes a slice of integers. It sums them in a for loop and returns the result. And now a little difference. Here you can see that I added a pointer to the argument. So each member of the slice is a pointer. So here I need to dereference the pointer in each of the iterations. I also tried with linked lists. So I put the numbers into a linked list and I iterate over the nodes and sum the numbers in the linked list. So and another thing I need to make sure is to explain is how the data is made, because in the normal case of a simple slice, it doesn't really matter. I just iterate over the slice, and to the nth element I put the number n. But in the case of pointers, I can have different strategies where to put the pointers, how to make the pointers. In the simple case, I allocate them one by one in a for loop. So in practice, they end up close to each other in memory, like one next to each other. So this is still quite good. But instead of this allocate int, I can have a more elaborate method which allocates the integer on the first line of the function, and then just does some allocations to confuse the compiler to not immediately optimize it out. And for the linked list, it's also easy. I just allocate the nodes next to each other, so it's the simple case. But in the results, you can see that the simple case, the blue bar on the left, is the fastest. But you can say, well, it's not that bad. Like it may be like 2-3 times worse, but it's not the end of the world. Here are the results next to each of the code samples. So the worst one is the linked list one, which is 3 times slower, and the slice where each of the elements is allocated quite far from each other is also quite slow. And I have 2 more examples. I did like another attempt of putting the data quite further apart in the memory by introducing a S32 and S128 structure, which has some padding. So if I allocate the structure, it will have the value and it will be padded by a number of bytes in between. Yeah, so it's not that bad, but if on the top you can see this is for 30K elements, 30,000 elements, just a little bit over 30,000, so that it's a prime number. for some reasons that I wanted to shuffle the numbers after, and with prime numbers it's easier. But here, cache actually helped us. It didn't all fit into L1 cache, but some of it fit into L1 cache, some of it into L2. But what if we increase the number of numbers? So here it's with 223 million elements, and the numbers are very different. The fastest one with 86 milliseconds is the one where we use some numbers one after each other. But once you put it into pointers, it gets a little bit slower. Not too much, because you just need to iterate the pointer slice and the actual values, which are also stored next to each other. But if you interleave them, if you do some allocations in between, it can get much slower. Like here, it's basically 173 times slower in this test. The linked list is also quite bad, but this is an illustration of if you have the data scattered all over the memory. If you allocate one piece, then do some network request which allocates a lot of data, and then allocate another element of the array, this can get really bad. So this is the graph that shows you how bad it is. Like I don't know if you see the blue line here, that's the fastest method, and these big lines are how long it takes in microseconds, the bigger one, or milliseconds, the less performant cases. And we have other things we can observe if we want really performant code. That cache is not a simple store of bytes. You don't have a cache filled with like random bytes from memory. You always fetch some consecutive number of bytes. In most CPUs, it's 64 bytes or 128 bytes. And if you fetch any data, for example, these 8 bytes here, or like 4 bytes from end of one cache line and 4 bytes from the beginning of another one, you always have to fetch the whole cache line. So you waste a lot of data. It's not visible here, but it's like light purple color is the wasted bytes that you read from memory, even if you don't need them. So if you can, it's ideal to pack as much data next to each other, data that you access together, and then you will waste as little cache as possible. And if you want to ensure that all fits into one cache line, you have to align it to the size of the cache line. And like an even more advanced topic is that each cache line can cache only some memory locations. In most processors, cache is like 4 associative or 8 associative, which means one memory location can go into one of the 4 cache lines in the processor, or one of the 8 cache lines in the processor. So if you have data that is, for example, 32 megabytes apart, or let's say 32 kilobytes apart from an L1 cache, it's highly likely that they will push each other out of the cache, because they have like the same end of the address and they go into the same line. So if you read one of them, the other one will get out of the cache, and vice versa. But this is an advanced topic. It's more like a side note. But another topic is aliasing, and I introduced it here so that I give you one more argument why not to use pointers if you can avoid it. Because if you pass a pointer to a function, the compiler doesn't know where it points to. It can point to something that's modified through some other way. For example, here I have a simple function that sums 2 slices into a third slice. In the first example, the size is passed in as a simple integer. In the second one is a pointer to integer. And you can see that the performance is worse in the second in the second case. So the first case is like 369 microseconds. The second case is 471, and the third one, which is a bit evil, is even slower. And why is it evil? That's to demonstrate the aliasing. Because in the third example, the size is actually stored inside the slice. So while overwriting the slice, the slice C, we are potentially modifying the end condition of the loop iteration. So the compiler, in this case, in the first case, the compiler can very simply make predictions about how many iterations it will do. It doesn't have to check after each iteration, am I done yet or not? It can just continue until the parameter it got from the input. But in the last case, after each iteration, it needs to check, is size still greater than I? And at one point it will not be, because or might not be, because the array is going to be changed. And this is a general problem. Like whenever you pass a pointer to a function, then anything of that type, if it's a pointer to integer or pointer to string, like any string can be modified by this. Any string that's passed in from the outside to this function. So every time the compiler has to re-verify that the string didn't change. So this is one more thing to keep in mind. And there is a simple solution. Like if you can avoid using a pointer, this will help you. Because if you pass it by value, there can be no aliasing. So the compiler can do much more optimizations. So this is a graph how it looks like without aliasing, and with potential aliasing, and with real aliasing. And another thing to keep in mind is where you allocate the data. If you allocate it on stack or on heap. If you allocate it on stack, the stack is basically put into the stack next to each other as you declare the variables. So it will be good for memory locality. It will be next to each other, which if you have really huge data sets, it's not just important for caching, but also for paging. Because another topic which we didn't talk about yet is that if you run out of real memory, the memory is going to be stored on disk or SSD. And it takes even much longer than getting it from memory. But every time you access a page, which is usually like 4 kilobytes or can be like 2 megabytes or even 2 gigabytes, you read the whole page into memory. So another argument why to put data that you access together, how to put them close to each other. So these are the takeaways that I talked about. Like if you can avoid using pointers, except if not using pointers would result in copying a lot of data. It depends on the benchmark. It's the best to benchmark it, but often even like a kilobyte a value that's 1 kilobyte long, it can be cheaper to copy it on like every function call if the function does a lot of calculations than passing it by pointers. If you need pointers and need to allocate data, it's better to allocate them, to pre-allocate a big chunk of memory and put the data into it next to each other and then make pointers to it. It's better than to allocate pointers where each allocation in between there is a lot of some processing like network request, which allocates a lot of heap memory. And also if you have some big structure and you iterate over a lot of these structures, sometimes it's good to extract the elements that you use often outside of this structure and put it into a separate slice, because then the data set gets much smaller and you don't need to interleave it with data that you don't use. And if you can, small values is good to allocate them on the stack. And if you really need performance, you can align the data to the cache line and try to use as much of the cache line as possible. And as a bonus, if you avoid pointers, you also get some safety, because if you call a function with a pointer, the function can modify the argument via the pointer. And you have to be very careful about making it obvious to the caller that it's possibly modified, or not modify it, and or have some culture around it. But if you pass it by value, it's easy. The function cannot modify the argument. So that's it from me. So thank you. And now if you have questions, you can ask questions.